starting with just the basics. So Mathematica works in cells. You don't run all of your code at once. Whatever you write goes into a cell, and you can see on the right it keeps track. Really basic. These are, I'll tell you the comment. And then down here I'm starting a new cell. So I'm just going to put output equals XYZ. And if I press Shift Enter, it prints out whatever I put in. Then I can set x equal to 3 and it'll print 3, one cell at a time, as you can see. And then if I print x plus 5, it'll print 8. But you have to watch out, if I go back and change x to 4, but don't reevaluate that cell, down here, x plus 5 will still be 8. Do you see what I mean? So it has good and bad parts there. It'll print everything you give it unless you put in a semicolon at the end. That tells it to just hang on to that. And then, very popular, the imaginary numbers are great in Mathematica. If you press escape, double I and escape again, you'll get your fancy I. If you want to use the regular keyboard, it's capital I for Mathematica. So don't label anything else by big I. It won't work out properly. Anything you give it, it will automatically simplify for you without asking. So I was printing out the last few things I wrote there. And yeah, it'll simplify for you by default. The other nice thing is that everything looks great in a Mathematica notebook. You can get the Greek letters really easily. So the same thing again, pressing escape and any letter, or escape and typing out a Greek letter gets you everything you want. You can get familiar with all the shortcuts. They're all there. Another bit of nice notation, I suppose. The operations are really simple. They're exactly what you expect. So x squared is just x there, but you can write that much nicer as x. And then if you hold Control while you're making those commands, you'll get your nice superscripts and your subscripts as well. And same thing for fractions. This will work fine, but you can also hold down Control before you click and get all the nice notation. Okay. So as far as commands go, they're all really straightforward. They're what you expect. Capital letter, and then basically just give it whatever verb you want. Square brackets, and then put whatever you want inside. So, for example, solve. What do I have? Got y squared minus 2y plus 2, and then I put in a double equals when you're setting an expression to be solved. That's important. And then I have a comma and what I'm solving for. And now when I go ahead and press Shift Enter there, it gives me my two solutions. And you can also get it to it can follow commands when they're written afterwards, like this. So if I do a squared plus 2a squared, 2 slashes at the end, and then, for example, full simplify. It'll simplify down for you anything that can go afterwards. A couple other notation notes and pitfalls. You need to have spaces between your variables or it will read them as one word together. So, for example, half mb squared is not the same as half mb squared. And when you evaluate that, you will see that. Okay, so since it's so simple to apply any command you can find, using the Mathematica documentation is really important. So on the Wolfram website, you can search for anything you want to do, and it will give you a load of different options. This is where you can find out what Mathematica is capable of as well. So if I just go in here, I search cross product, and in every section it has this. So up the top, a simple explanation. If you're into programming, you can look at all the details of everything. The best part is this, your examples that they have written for you. Super helpful to implement things quickly. So it does have examples for you, simple ones and then more complicated. And then down the bottom, they have scope of how far this goes, and properties, relations, other places you can use things. You also pick up other commands that you didn't know existed in here. And sometimes at the end of this, depending on the section, some of them will have a last one here that says neat examples, and you can get good stuff there too. So becoming familiar with that website and using it to your advantage is very much key for Mathematica. Okay, for the next section, I'm going to show you how to use vectors and matrices. So it's curly bracket notation. I'm going to define sigma x, sigma y, and sigma z Pauli matrices. Curly brackets to open, and then curly brackets for each row within. So in this case, it's going to be curly brackets and then 2 rows, sigma x, 0, 1, 1, 0. And I'm putting a semicolon at the end, so it won't print everything. Sigma y is the same. I'm using imaginary numbers here again. And finally, sigma z. 1, 0, 0 minus 1. Now for this one, I'm going to put the command at the end matrix form, and it will print it out in nice matrix form for you, so you can, get a good look at things, and you can, if you're going to be like typing out assignments in Mathematica, it'll make everything look nicer. However, it can't evaluate matrices and vectors in matrix form. That is purely for viewing purposes. When I go to, I'll say sigma x dotted with sigma y, dot product is just full stop in between. It can print that out fine. But if I say sigma x dotted with sigma z, it won't do it for you because it's like multiplying with a picture. So watch out for that. Then one of the most useful things in all of this is the eigenvectors and eigenvalues. So if you just say eigenvalues of sigma x, it'll print them for you, and you can print the whole eigensystem, and that'll give you the eigenvalues and the eigenvectors that go with them. Obviously it doesn't label them, but if you look at the website and all the documentation, it'll be very clear what corresponds to what. Eigensystem is a really important function. And the one that I was just looking up before was the cross product. As you saw on the website, you could just put cross and then your bits inside there, or you could do matrix backslash, or sorry, escape backslash cross. There are shorthand commands for all of them if you wanted to look neat and tidy and put a little X in the middle. Okay, then, do you guys have Mathematica on your devices? Yeah? See then, with the solve function that I gave you and with the notation for matrices, if you can solve this system of equations. So you know it's capital S solve, square brackets, and you put what you're solving for after the comma, and if you're solving for multiple things, you put it in curly brackets, just to make a little list. So you can put alpha, beta, and gamma in there. And you can set up the have a go at setting up the matrix equation using curly bracket notation. So if you're stuck on the notation, that's what you're looking at. If it's all in correctly, it should print out a really nice, neat solution for you. Alpha goes to 5, beta goes to 3, and gamma goes to -2. When you first print that also, sorry, I wrote weird stuff up there. When you first print that, it will make suggestions to you about what to do with your answer, which is pretty handy. So you can then, sub them back in. There's an automatic command for that. Sometimes it'll offer to plot them or label that a first solution, whatever it is. Okay, then back here, next section, I'll talk about the calculus functions. So derivatives in Mathematica, really simple. Capital D, then put in whatever you're going to differentiate. So differentiate x squared with respect to x. Sorry. I've already labeled x elsewhere. That's what that's for. And very straightforward. You can also integrate, of course. Command, integrate. And if I integrate 2y with respect to just y, it won't put in its plus c, it won't reference the fact that it's missing anything. It'll say it's all fine. So it's most useful in a range. And like before, expression, comma, where you're doing it, curly brackets on the outside of anything that needs more than one piece in its place. And just to give you an example of how useful this can be, if I tried to integrate this big thing, logs, everything, they're all in basic Mathematica language. You don't need to download a package or anything like that. 1 plus square root, control 2. And I'll integrate with respect to a between 0 and 1. and it's doing really quick integrals for you. It's built-in simplification, very handy. Yeah.
Is log base 10 or base e Mathematica?
Sorry?
Is log base 10 or base e Mathematica?
You will find it in your documentation. Let's check. I assume E. So log gives you to base E, and you can look up the command for base 10. Okay, and then with your ability to differentiate and integrate big things really quickly, you can go on and do all sorts of nice stuff. But for now, let me define a couple of functions. If I label the function f, I want v to depend on t, and vt squared plus 5. The squared needs to go after the dependence, not in here, or one word. So I'll put that through, it'll simplify, and then take the derivative of f with respect to t. And it does really nice derivatives for you, it gives you primes as its notation. So that's how you would call on a function that's just an expression, but to write a function that can take on any value. Same thing, label it whatever you want, square brackets, but this time, if you put underscores in, and a colon equals, you'll get a proper global function that you can call on any variable. So I'll define it to be a minus b squared. Now that obviously won't print anything, but if I put in h of 4 and 7, it'll call it for me memory. A useful thing when you're writing lots of functions, question mark function, it'll tell you the details of the function that you're looking at, just to be handy. For an ACM example, I think. Yeah, if I take these guys, this is how I would be using Mathematica. So with the Lagrangian, half ml squared, theta prime of t squared plus sine, again, capital letter, and then it has everything. Just put in all your t dependencies, and I have a semicolon at the end, so that won't print. And then I'm going to construct the equation of motion. So it's really straightforward. Derivative of L with respect to theta of t, 0. Derivative of L with respect to theta prime of t. Oh, have I done something wrong? Get rid of these. Sorry. Hadn't ran the cell. And you can do all the others. Derivative of L with respect to I of t, and derivative of L with respect to I prime of t. and take a second derivative of the Lagrangian with respect to theta prime and theta of t. So the first time you're taking it there, and then with respect to time again. So each time you have your square brackets, you do need to have a variable that you're differentiating with respect to on the outside. So from those, you can really quickly construct your equations of motion for advanced classical mechanics. Okay.
Did you then like expand that for like small numbers?
Sorry?
Did you then expand that like to something like Taylor series using the program?
Yeah, it has Taylor series. Let me see. So you have expand functions that you can put after anything, and for the series functions, there's something I didn't include in the tutorial, but they are very good. They can do out a little series for you, and you can preset how far you want that to go, like here. Give it a start point and an end point, make it as accurate as you want it. Then probably the most useful part of Mathematica, maybe I said that already, but plotting. Mathematica makes really nice graphs, and even if you don't use it to code anything, you'll probably look for somewhere to print out a nice graph at some point. So same as before, capital letter, square bracket, and then you can print anything you want. So I can print plot x squared, just put any expression in there, or if you had labeled something else, obviously you put that label in there, and you need to give it a domain. So I'm plotting with respect to x between -10 and 10. And the plots are very nice, but they are default plots. If you want axis labels or different colors or legends or anything like that, you need to tell it. And as soon as you write plot in here, it starts giving you all sorts of suggestions. So let's say plot range, and more suggestions. Let's say automatic. It goes to 100 automatically. I could say axis labels. I'll give them the automatic ones. Updated to have X there, and you can also have plot style, and I think font size goes in here. Yeah. I don't know if that worked properly, but everything's in there anyway. You can change the colors, and when you get more advanced plots, you can make them good enough to be in a capstone project, which is great. Not just the plot function though, but the good stuff comes from its like derivative commands. So plot 3D will give you obviously a 3D plot. So if you plot x squared plus y squared, this time you need to give it its two variables, so I'll go -5, and for y from -5. Makes a very nice plot for you, and you can spin these around as well. So they're good for visualizing any homework question, any function you're ever given. And the same thing goes in here. If you want to add any more details to your plot, you just go ahead and do it. So I'm going to put a name in here. Put a tag, anything you need. Then, as a neat example, as Wolfram says, I'm going to define S to be the solution to an ordinary differential equation. So ND solve gives you a numerical differential solution to, I'm gonna have two things in here, so I need curly brackets. Y prime of t double equals again y of t plus t plus y of t. And second one, y of 0 equals 1. So you list all of your equations that you want solved first in the first section in curly brackets, then the variable that you want to solve them with respect to, and it expects another variable here too. Let's see if that works. Now if you get a weird solution that you won't be able to do anything with unless you plot it. So let's try plot. I'm going to plot two things now. I'm going to plot y of t and y prime of t on the same plot. I need the same thing again, t between 0 and 20. Now it doesn't know what to do with that either. However, since we labeled ND solve the whole set of solutions, the interpolating function S, this command says replace these with S. So /dot is very useful. So you're replacing what you had put in before with something useful. Now this is not the next best way to plot these solutions. A better one is parametric plot. So if I make a parametric plot of the same thing, make all this, get a really nice plot of your solution to your ODE. There are, I don't know how many types of plots, but if you search plot on the Mathematica website, you will get so many different options. Another one that's used very often is list plot. If you're plotting from a table or a list or a set of values instead of something like a function, then you can list plot to get points instead. So I'm going to plot from the table of, this is also how you make tables. I'm going to make a table in 2 dimensions, a squared and a, with a running from 0 to 10. So it has made a table. I can get it to print that table too, or just go ahead and plot the whole thing. And then you get nice points. I think those were all my main points to make. That's the full solution for that was the full solution from the ACM example. But if you can ND solve this and parametric plot it, you have made good use of Mathematica for undergrad anyway. Sorry, so for this one I desolved. So I didn't look for a numerical solution, I just looked for a differential solution, and it gave me this. So it gave me a solution in T, and it gives constants, so it labels constants C1, C2, etc. You can take this, and if you have more information, solve for that constant, but I just took this in here to plot, and took out the C1, set it equal to 1. And you get more very nice plots. I think those are main points. Anyone have any particular question, or I can show you some more advanced pieces. Okay. Okay, these are some bits from my project, so I'll just pick out a couple of functions that might be useful. My project was about classical and quantum oscillators, and I was synchronizing systems of them. So here is a for loop in Mathematica. Probably wouldn't use this unless you're looking to, program properly using Mathematica. But the notation is there for whatever, from whatever to whatever, and then everything you want it to do at the end. Also an example of something, another good feature. It can take random variables for you. It can take them from any distribution you give it. They're all built in. Then here I'm making a table of all these values to then use them later, plot them later. And the dimensions of the table are from 1 to number of oscillators. And there at the end I used ND-solve since the model I was using was solved with a differential solution. And this plot at the end, that was in my project, it shows where 100 oscillators, if they started all around a circle, but they're coupled to each other, they in time come together and synchronize. So in this case, I had set k equal to 1 up the top. K was how strongly they're coupled together. Then obviously I wanted to look at how it changed as you changed k and make k a variable. So that is when module comes in. Module is the option in Mathematica for creating a cell where everything in it depends on a variable, I suppose. You list the variables that you want to hold at the start, and then you can do everything inside. So I created a table, I have a for loop, I'm solving a differential equation, and I'm updating that table. And then at the end you can see the replace there too, replacing what it started with the solution. You can do all of that inside a module, so if you're going to properly program, that'll be really useful. A couple other bits. The 2 square brackets there and the 1, that is telling it, so when we're printing out lists and matrices and stuff, there are curly brackets. You're asking it to go to the first one and the first line, if you get me, come in how many curly brackets. They start to build up, and you still get your right answers, but if you're trying to call on it later, you want to be calling on exactly the right value, so that's what that's for. And then down here, I use the list plot. So at the end there, I have data plot, analytical plot, and show. I put the semicolons after both the plots, and then when you say show, you can save everything and print it at once at the end. So the reason I did that was to layer 2 things on top of each other while they were calculated separately. It's a pretty handy feature. Then a couple other bits. There's a command for everything you can think of. This one is diagonal. It just takes all the diagonal elements of a matrix for you and keeps them in a list, basically. So I use that quite a bit with my density matrices. Evaluate can be handy if you're saving stuff and not evaluating until later. When you do go to do that, you use evaluate. More nice plots, this time with a legend. And finally, I defined any functions that I needed that weren't already in Mathematica, like the commutator, and the lid-lad operators. Proper quantum mechanics operators, I wrote them in myself using the colon equals kind of functions, and then called on them all later. And as you can see, I have all my matrices in the not good looking form because they're useful, and I have another big module at the end. So there's a lot of thought and work that just gets condensed down to, what, 8 lines of code. If you're doing it right up until that point, a lot of the issues come from your tables being of the right dimensions. When you're calling on something, you're calling on the first row when you meant the first column, things like that. The speed of it, as you saw with like a decently difficult integral is fine, but sometimes it can take a while to do, I don't know, something more complicated and longer integrals. It can be coming out with solutions in that C1 constant it gave. You can have 10 of those and it labels them all separately, so it takes a while, and then your answer isn't particularly useful. So there are some pitfalls for sure, but hopefully you can make some use of it and appreciate the power that Mathematica has for anything. Last one, the final culminating result from my project, and it was copy paste straight out of Mathematica. Makes a really nice contour plot. So it is capable. You can get good stuff. And that's it. Any questions? Okay, thank you.
Sorry, just very quickly, is there any other good resources online that you can learn Mathematica from?
There is, well, I don't know about learning it from the start, but the Mathematica Stack Exchange has its whole own section.
Sure.
You can look up any problems in there. It seems overcomplicated a lot of the time. If someone uses this as their primary programming language,
Right.
they get into all sorts of fancy stuff. When for us at undergrad, it's mostly like a fancy calculator, to speed things up. So I wouldn't get too bogged down in like the way they code on here, but it can be good. Yeah.
I got a question. Is there a way to make an animation like
Yes.
interpret? Yeah. So, like the face-based part you just made by magic part. You can make it move, right?
I think so. I forgot what the command is. Maybe this is just for storing this, but I've seen moving. Oh, they're just imported. Definitely seen moving plots before.
There's animate and there's list animate as well.
Animate. Yeah, so you can create a plot here that will, if you have that in your program, it's interactive and you can scroll through, you can increase and decrease values. It was something I looked at doing for my project, but decided not to because ultimately it's not useful for a report, but would be good for a blog or a website, I suppose. Anything where you could actually present it.
Positive, like in ACM, you have trajectory, say, a simple positive. Like this side, you only get twice all that if you want to like show the same.
Yeah,
It's all that.
I think it should have the capability.
Does that like this?
Some neat examples. So they're solving for something there, and then animating a table out of the solutions. The color plots are good too. You can show anyone that did the Rory's thing, the counties, when we looked at electoral boundaries, and you're looking at the color plots to show the sections coming together nicely. There are functions for that kind of thing to make nice plots. There's also there's specifically a map graph where you can when you see those plots like all the countries by education, and then you see the hotspots, you can make those really nicely in Mathematica. I think it would be quite useful for anything you need to produce for a presentation. It's a good way to get nice plots, I think. Nicer than Python. Hot take, but I think it's pretty good. They look nice and they're much faster to manipulate and easier to look up cool stuff, I think. Anything else? Oh, okay. Thanks, guys.
Thank you.